Welcome to this explainer. I'm so glad you're joining us today because we're going to dive right into something that is absolutely crucial in our modern world, taking raw, chaotic numbers and transforming them into powerful visual predictions. Look, we live in a world that is just completely swimming in data. But on its own, a giant list of numbers doesn't really tell us much. It's just noise. So today, we're going to look at how we can organize all that noise, uncover the hidden stories inside it, and actually use those stories to predict the future. Now, right off the bat, think about this question. How can the temperature outside predict the number of ice creams sold? What's great about this is that it instantly grounds the math in a totally relatable real-world scenario. We inherently know, just from common sense, that a hot, sunny day makes people want a cold treat. But as problem solvers, we don't just want to rely on a hunch, right? We want mathematical proof. We want to know exactly how many ice creams we're likely to sell if the thermometer hits, say, 25 degrees. This simple question is our perfect gateway into understanding how different variables interact with each other. To get to those answers, we've got a really clear game plan. We'll start by mapping out the raw bivariate data, then move on to identifying correlation, drawing our line of best fit, seeing how graphing calculators do the heavy lifting, and finally, making those predictions. Okay, let's jump straight into section 1, mapping bivariate data. This is really the raw material of our whole journey. Before we can analyze a single thing, we have to understand the specific type of information we're actually dealing with. Whenever you're collecting two connected variables to plot on a scatter diagram, you are dealing with bivariate data. And it's literally right there in the name. The prefix bi means two, and variate refers to the variables. For example, imagine you're measuring the height and mass of a group of children under 5. By taking those two different measurements from the exact same child, you create a connected coordinate pair. We aren't just looking at heights all by themselves or masses in a vacuum. We're looking at how they exist together. And here is a brilliant illustration of that raw material. In one column, we've got the temperature in degrees Celsius, and in the other, the number of ice creams sold. Each row represents a single day, giving us an X and a Y value. So at 15 degrees, they sold 8 ice creams. At 24 degrees, they sold 34. This table is bivariate data in its purest, most basic form. But let's be real, staring at a table of numbers isn't exactly the best way for the human brain to spot a trend. For that, we need to visualize it. Which brings us to section 2, identifying correlation. Let's see what happens when we actually plot this data out. When we take those pairs of numbers and put them on a scatter diagram, the magic really starts to happen. Generally, the points are going to fall into one of 5 distinct categories based on how they lie. We call this relationship correlation. So if both values go up together, like temperature and ice cream sales, that's a positive correlation. If one goes up while the other drops, that's a negative correlation. And if it just looks like a random cloud of dots scattered everywhere with absolutely no rhyme or reason, well, that's no correlation at all. But we can break that down even further. Notice how we visually distinguish between strong and weak correlations? Strong simply means the points are tightly packed together, practically hugging an invisible trend line. If the dots almost form a perfect straight line going diagonally, you can be highly confident in that relationship. But if the dots are spread out, loosely drifting in a general direction, that's a weak correlation. It tells us, hey, there's a relationship here, but there are clearly other factors at play too. Now for section 3, the line of best fit. This is the tool that cuts right through all that statistical noise. This is where we bring real order to the chaos of our scatter diagram. Now, if you're drawing this manually, you can't just wildly sketch a line through the middle of your graph. You have to follow 3 strict rules. First, your line has to stretch across the entire set of plotted data. Second, you want balance. Roughly the same number of data points should be floating above your line as there are below it. And third, to anchor it perfectly, you need to calculate the average of all your X values and the average of all your Y values. That gives you the mean point, and your line of best fit must pass squarely through it. I do want to point out a very common pitfall here. A lot of people feel this overwhelming urge to start their line at the bottom left corner, the 0, 0 origin. Don't do it. The line goes strictly where the data dictates. And similarly, your line of best fit might not actually touch a single one of your plotted points, and that's perfectly fine. Remember, it represents the overall average trajectory, not the individual specific instances. Moving right along to section 4, graphic calculators in action, let's see how we automate this. While drawing by hand is fantastic for understanding the underlying mechanics of what's happening, in the real world, we rely on technology to do the heavy lifting. Here we see the digital leap. You just enter your temperatures into list 1 and your ice cream sales into list 2, and graphic display calculators instantly transform it all into a scatter graph with a precise regression line. They don't just plot the points, they calculate the exact mathematical equation for the line of best fit. It completely removes human error and gives us absolute mathematical precision. And finally, Section 5, Making Predictions. This is the ultimate goal, folks. This answers the big why. Why do we go through all the trouble of mapping bivariate data? It's not just to make neat-looking graphs. We do it to gain a superpower, the ability to estimate the unknown. Because once you've established a solid pattern, whether it's weeks of ice cream sales or anything else, you can make a mathematically sound assumption that new data will adhere to that exact same invisible rule. The line of best fit empowers us to predict outcomes we haven't even seen yet.
So how do we actually do it? It's incredibly straightforward. Let's say we want to estimate sales for a 20-degree day using our ice cream graph. You simply find 20 on your x-axis, draw a straight line straight up until you hit your line of best fit, and then trace exactly across to the y-axis to see the predicted sales figure. Just like that, you've turned a scattered history of past data into a literal crystal ball for the future.
To wrap things up today, I want to leave you with a real-world scenario to test your own predictive powers. Think about a car's engine size and its fuel consumption. How do those two variables interact out on the road? If a car has a massive, powerful engine, does it consume more fuel or less? Ask yourself what that scatter diagram would look like in your head and whether it represents a positive or negative correlation. Thank you so much for joining me on this explainer. Keep looking for those hidden patterns in the world around you, and we will catch you next time.